lensing or demonstrated, I think. Well, goodness, John, that had to have been in the late 90s when we were
Yes.
in that together. And then we kind of went our separate ways. He continued to work on the James Webb Space Telescope, and I ended up in planetary science and down at NASA headquarters. Um, but one of the most I should just as a formality, his background is he has a BA in physics from Swarthmore and a PhD in astrophysics, I believe, from Berkeley. And has spent, as best I could tell, most of his career as a civil servant, meaning he works for the US government as part of NASA. And then in 2006, because of some of the work that he has done on a mission called COBE, and I'm sure he'll talk about that, he was nominated and won along with George Smoot. They won the Nobel Prize in physics for their understanding of, I think it's the anisotropy of cosmic background radiation. So maybe we'll learn a little bit about cosmic background radiation as well today too. With that, John, I'm going to give you the floor. Go ahead and take 30, 40 minutes, and then by then we'll have lots of questions. And remember to share your screen.
Okay, lovely. Thanks for the introduction, Jim, and for our long and continued friendship with many, many beautiful kinds of science to think about. So here is my sort of summary of what I want to talk about today, from the Big Bang to quantum everything to life. So not just how did the Big Bang work, but how did we get here? So as a child, I was fascinated with this question. I had heard about Charles Darwin, but it was even obvious even then that nobody knew how that all got started. So now we have a little bit more information to tell you about, and we have some awareness of the story to think about and some areas for all of you to pursue as you grow into practicing scientific adventurers. So well, I'll start with a picture here on the front, however. This is the great James Webb Space Telescope as we imagine it to be in outer space. You see this huge hexagonal mirror. It's made of 18 smaller hexagons. They're all made of beryllium coated with gold because that's the best reflector for infrared light. And the gray object you see beneath the telescope is actually a 5-layer umbrella, a sunshade, to keep the sun off the telescope and let it get cold. Because this was the telescope that was built to study infrared light that you could never study from the ground. And you could never study it with a Hubble Space Telescope because the Hubble is warm and it glows. It emits its own infrared light. So that's what made us famous in recent times. It was launched on Christmas morning, December 25th of 2021, and it is working beautifully. We're so thrilled with this incredible engineering job that has enabled wonderful discoveries in science. So backing up a little bit from all of that, just a little bit about how do we know things. So everybody knows now that the universe is expanding, and how did we find that out? In 1929, Edwin Hubble drew us this graph, and each of those little dots is a galaxy. As you know, a galaxy is more or less 100 billion stars held together by gravity. And excuse me, these we were just beginning to be able to estimate the distances of galaxies. So he put his estimated distance on the horizontal axis. And we also knew how to measure the velocity of a galaxy coming toward us or away from us. It's done with spectroscopy because each chemical element emits or absorbs light at particular wavelengths. And if you look at a distant object, you'll see the wavelengths are all stretched out. And so we attribute to this to a motion of the object going away from us. And we now can say, well, how fast is it going? So even in 1929, we could draw this first graph, and you see the obvious trend here. The farther away they are from us, the faster they're going away from us. Divide the distance by the speed, and you get the age of the universe. So 1929, the same year that the worldwide economy collapsed because of mismanagement and optimism, but we discovered something perhaps even more surprising, that the universe is expanding. So it had been predicted by mathematicians, and George Lemaitre was actually a Catholic priest as well as a PhD physics professor, and he had predicted this in 1927 based on Einstein's equations. Einstein did not expect this and was completely amazed and did not quite even believe at first. But anyway, uh, first time we knew the universe has an age and is expanding. So a little bit about quantum mechanics, because that's also about a century old. Here I've got a picture of Erwin Schrödinger, who is the person who gave us a wave equation to describe the motions of objects. So what did we find out? We find out that everything we've been calling particles is actually not really particles, but is waves. Excuse me for my telephone. We find out everything is made out of waves. So what we called a light wave, we already knew light was waves, but we found out also that electrons, protons, neutrons, nuclei of all sorts, many other things that are combined to make those objects are also waves. So Schrödinger gave us the wave equation. These waves are described by complex numbers as a function of space and time. With those equations, you can find out, after a lot of work, pretty much everything there is to know about what we call particles. But actually, when we call them particles, we are fooling ourselves, because when you think of a particle, you think of an object that has a position and a velocity. But a wave packet does not have a position and a velocity. It's spread out in space and time. So why do we call it quantized? Because when you trap a wave, as for instance, a electron wave around an atomic nucleus, those adopt the solutions of Schrödinger's equations have particular energies, and particular shapes. So those can be called quantized. That's how we proved that it was right. Schrödinger's equations describe molecules and atoms very beautifully. Then over the following century, we found out about the particles that go inside. But to summarize all of this, everything you see is not particles, but waves. And there's a lot of interpretation questions about this. But we have hearing a lot about probability and quantum mechanics, but I think really we should just think about waves. So there's a reference for you if you want to pursue this a lot further. So then here's a standard chart from particle science, particle physics. We've got a list of the different kinds of particles. But again, we're calling them particles, which is always deceptive because they're not particles, they're waves. So this is the different kinds of wave packets you can have. The quarks are the constituents of atomic nuclei and protons and neutrons. The leptons are very much lighter weight particle waves. We've got a few flavors of them, basically electrons and heavy particles, and neutrons and their heavy versions, plus many other things. So it takes a lot of math to do the depth of understanding that you would like to have about these things. Just all I really wanted for you to know today is there are no particles, there are only packets of waves. And you can get the math and you can work it all out. And so plenty of mysteries, but thank you. So what is still mysterious about that? Well, there's plenty of things unknown in astronomy and physics, and here are some of the biggest ones. We have found out from astronomy that there is something we call dark matter, which is, we don't know if it's a wave or a quantum field or whatever it is, but it has gravity and affects the orbits of things. It can bend light. So that's how we know it's there. And we're very sure of that. And we've been having evidence of it since 1935. So still don't know much more about it, but we know it's there. There's something called dark energy, which again, we don't understand, but it makes the universe accelerate and go faster and faster every year. And the Nobel Prize was given for discovering that. We have a mysterious force we think might be right called cosmic inflation, and would have acted in the first sub-microseconds of the early universe, and it would explain the uniformity of the universe, the fact that it seems to be almost the same everywhere, and would also explain why we have spots in the cosmic microwave background radiation, which is very strong evidence for this. So we think it's true, but we can't prove it very much. It's not necessarily the only thing that could explain it, but that's a part of our amazing story. Finally, we have the curious asymmetry between matter and antimatter. The fundamental equations that we have that describe particles and wave packets seem to be symmetrical between matter and antimatter. So we don't understand why we have more matter than antimatter, and we are still here, and there's no antimatter anywhere else in the universe except momentarily. So, and finally, if this is a great dream of physics, if you could explain the fundamental constants of nature, the fine structure constant, the gravitational constant, the reasons for the charge of the electron to be what it is, those kinds of things would be very great proof that we have a very deep understanding, and we have not any way to do that now. So it might take us a month, or it might take us a century to find those answers, but I think we will find them. So here is the Cosmic Background Explorer satellite. The way that this happened was when I was a graduate student in Berkeley, we set off to measure the spectrum. That is to say, how bright is the cosmic microwave radiation at all wavelengths, using a balloon payload, basically a satellite hanging from a string at high altitude. And our experiment eventually worked, but not in time for me to write a thesis about the working experiment. I got to write a thesis about a non-working experiment. So, however, I got a job at NASA to become a radio astronomer. And 6 months later, NASA said, we want proposals for new satellite missions. I said, boss, my thesis project failed, but we should try it in outer space. He said, that's right. We will call up our friends. We will write a proposal. And we sent it into NASA. And I thought, well, that'll never work, but might. So 15 years later, this satellite was launched into space to measure the cosmic microwave background radiation spectrum, and also to make a map of it to see if it's equally bright in all directions, and even to look for the cosmic infrared light that was predicted to come from the first generations of galaxies. So it went up, and because it was built by professional engineers, it worked beautifully, and within weeks we were able to confirm the predictions of the expanding universe story. The spectrum is perfect, exactly the way that it should be if it's the remnant of what we call the Big Bang. And we also predicted that we should be able to measure the hot and cold spots in this pattern of the microwave radiation from the early universe. So there's a map, the first one that we were able to make. It shows the universe having hot and cold spots when it was about 400,000 years old. That's the time when the heat of the early universe had diminished enough that hydrogen and helium atoms could be formed from hydrogen and helium nuclei and electrons. So the universe became transparent at that time, and light was freed to travel in all directions without hitting anything after that. So we now are able to look at this map, which is represent the entire sky, flattened out onto a flat surface so you can see it. And you see the hot and cold spots, which are very faint. The whole temperature of the cosmic background is 2.7 Kelvin, 2.7 degrees above absolute zero. And these spots are about 1 part in 100,000 different. So 30 microkelvin hot and cold spots. A true triumph of engineering to be able to make the map. And when Stephen Hawking saw this map, he said it was the most important scientific discovery of the century, if not of all time. So why would that be important to us as scientists? Well, number one, if those spots did not exist, we would not be here. The universe had to have some way to break the symmetry and say, well, some places are going to stop expanding, the material will stop expanding and turn around and fall back in to make galaxies and then stars and planets and people. So we are here because of those spots. Then there's lots more evidence in here about the cosmic dark matter and the dark energy, and perhaps some year we'll understand what made the spots in those very first moments of the expanding universe. So very, very important story about how things got started. And then, of course, you ought to be able to say, well, what happens next? So some things are predictable, at least statistically, and you ought to be able to measure and see the results of this story that we tell. So, of course, the Hubble Space Telescope was launched a few months after the COBE satellite, and they did as much as they could to see the very first galaxies. And they came to the immediate conclusion that the telescope was not the right telescope for that purpose. So as soon as the telescope was working properly in space, they wrote a report that said, please build us another telescope that's more powerful and can observe infrared light that the Hubble cannot see. And so here it is, as we've ended up building it, the James Webb Space Telescope. So it is an international collaboration. We led it from the NASA Goddard Space Flight Center in Maryland, just outside Washington, D.C., in collaboration with Europe and Canada. Of course, we hire a giant aerospace company called Northrop Grumman to build the parts that they can build, but the instruments, the cameras and spectrometers that record the images and send them back to Earth, those were produced around the world in various laboratories in Europe and Canada and the United States. So the telescope is 6.5 meters in diameter. It's made out of these 18 hexagons. It runs at a temperature of about 40 Kelvin, 40 degrees above absolute zero, so that it does not emit much infrared light. It was launched in a European rocket called the Ariane 5 from the country of French Guiana. It's on the north coast of South America, and it's almost on the equator. So it's a very good place to launch rockets from. And it did a beautiful job, and it put the telescope into orbit around a place we call the Lagrange point 2. So here's the diagram, not to scale. The sun in the center, the Earth going around the sun once a year, the moon going around the Earth, and then much farther out from Earth is the Lagrange point. The Lagrange point is actually at the end of the shadow of the Earth, so it's right in line there. It's a place where combined gravity of the Earth and the sun is enough to pull the orbiting object around the sun once a year, and so it stays there. It can stay there all year, overhead at midnight. It's a great place to put a telescope. For us, it's also valuable because the sun, the Earth, and the moon are all in one direction in the sky, and you can put up a sunshade, an umbrella, that will protect this equipment from the heat and the light of all of those three objects at one time. So it's about 1.5 million kilometers farther out from the sun than the Earth is, so about 1% of the distance from here to the sun. So pretty close by in terms of the solar system, but still much too far for us to go to with astronauts at this point. So we had to build it knowing that we would never be able to fix it or repair it. And that's why it's such a very difficult project to do these observatories in space. You can't fix them if they're broken. So what have we found? Well, we wanted to be able to say we have found the most distant, most early objects to form after the Big Bang. So here is the way we do it. We take pictures, take thousands and thousands of pictures of the sky, and once in a while we find something like this. That little tiny speck they've magnified in the image you see is a very red spot. And we say, well, that's a sign that this object is running away from us very fast. So then when we want to find out if it's really as far away as it seems to be based on the color, then we stretch out the light and take a spectrum to see does it have the characteristic patterns that it should have if it's really a very, very, very distant object. And certainly it is. Um, in this case, the thing is labeled with what we call the redshift, the Z of 14.3, which means the wavelengths that we observe are 15.3 times longer than the original wavelengths when they were emitted by the particular known atoms in the galaxy. So very, very far away. The universe was about 290 million years old at the time that that light was emitted in our direction. We have found something that we were all hoping to find, something that nobody had ever seen before. I call them little red dots because that's what you see. A tiny speck on the map. When you try to see, does it have a shape? Some of them are so small you can't see that they have a shape. Some of them are a little bigger, but they're about 1% of the size of the Milky Way galaxy. There are none of them left today. Nothing looks like that now. So what we are thinking of is probably a brand new galaxy with a black hole in the middle. Maybe the black hole is growing very rapidly. At any rate, these objects spin very fast. About 1% of the speed of light is the spin rate. And so this is a new discovery. They were formed within about 1 billion years after the Big Bang, and they've all disappeared or changed into something else. So we're very happy with our major discovery, and it has changed our story of the early universe quite a lot. What else have we able to do? This is an example of using Einstein's gravitational lenses. Einstein told us that gravitation would bend light, and he told us exactly how much. Even Isaac Newton speculated that gravitation could bend light, but of course, in those days, there was no hope of testing that theory. Now we have demonstrations. So what we're seeing in this picture is a very bright nearby galaxy. You see on the left the 3 very bright fuzzy objects. Then you see a strangely shaped pink arc or orange arc. And that turns out to be a magnified image, a distorted image of a single galaxy. And it's given us 3 images of the same galaxy. And we know it's the same one because there is a supernova, which you can see circled there with where it says a circle around point 2C or 2B or 2A. Those are all the same object seen 3 times. So this tells us many important and useful details about what's going on in the shape of the lens as well as the shape of the object that we're studying. So this is quite common if you look in the right place. See the distorted and magnified images of very distant objects. So we're using nature's lenses to help our telescope. This is one of our most famous pictures. This is called the Pillars of Creation. And this is a place where stars are being born today. In the picture, we see clouds glowing in space because they're being illuminated by bright stars that are nearby. It appears that there's a wind blowing through space, which is correct. There is a wind blowing through space. Space is not really empty. The wind is impinging on this cloud of material and changing the shape. And in a few places, you can see, I don't know if I can make my pointer point here. You see, for instance, up here, you see a new star that's just been born in there. That's just beginning to poke out. So this is a star formation laboratory. Hundreds of new stars are being born in there. And we imagine, although we can't see them yet, that there are planets being born around all of those stars as well. Here is a star that is being born much closer to us, so we can see the details. As you know, the solar system is flat. Almost all the planets orbit in a single plane called the ecliptic plane or the zodiac. And so here we're seeing a new star forming like that. There's a disk of material which is labeled here, and we see it edge on, so you do not actually see the star itself. But we do see jets of material coming out from the new star, as the label calls it, conical outflow. We think or imagine that there must be planets in there as well. And if you were to come back in 100,000 years or a million years, most of the dust would be gone and the planets would still be there. So we can't wait that long, so we have to find other objects to study. But this is clearly a fascinating example of new stars being born with all kinds of fascinating things around them. So we would like to know if there are planets like Earth out there, and we do know that there are many that are the right size and temperature to be like Earth. So this is what we can do with the Webb telescope. When a planet goes in front of a star, it blocks some of the starlight, we see that as the star gets dimmer for a while, and we can tell that the planet is there. Some of the starlight passes through the atmosphere of the planet if it has an atmosphere, and we can study that part. So we can now study at what wavelengths does that planet absorb light, and therefore deduce the chemistry of the atmosphere of a planet around another star. So this works very well for small stars and big planets. It does not work well enough yet for us to be able to study an Earth around a star like the sun. It's just too hard. So to study more about things that could be like Earth, we study things in the solar system. So this is the surface of Europa. Europa is a satellite of Jupiter. We sent a probe to orbit around it many years ago and took pictures, and we see that the surface of Europa is covered with ice. And there are cracks in the ice, and water comes out from between the cracks from time to time and tells us that those places might have molecules coming up from below that would show signs of organic chemistry. So we have sent already a probe to go there to find out. We have taken pictures of Titan, which is a satellite of Saturn, and it has an atmosphere enough to support a helicopter. We are going to look into that one as well. There's a probe being built that could land there in 2034 if we get to finish building it. So then we would know much more about that one. Now I want to talk about how do we have life? Where in the universe is it possible to have life? So what are the 5 instabilities that could lead to life that we have here? Well, number one, we told you about the expansion of the universe caused by this cosmic inflation. And that sets up the initial conditions and produces the elementary particles, or we should call them wave packets of matter. So that, that enables all of the chemistry and physics that you know about, because the parts are made then. Then the second instability is that gravitation always attracts, so that matter can be unstable. So when there's enough matter in one place, gravitation will pull it back, make a star or a planet, and then we can have the structures that you're familiar with. And then energy can flow out of the stars, and energy flows can support what we call spontaneous heat engines. A heat engine is some structure that takes an energy flow and supports something that you might be interested in. So for instance, a hurricane, a storm here on Earth, is a spontaneous heat engine. It draws heat from the sun through the surface of the ocean and circulates that in a way to make a very complex structure, dangerous structure, and actually increases the total entropy of the universe by doing that. So energy flows from place to place support complexity, because a complex system can increase the total energy, the total entropy of the universe. Then, because that's all possible, then we have organic chemistry, which, as it seems to us, organic chemistry based on carbon is the only kind that does this well enough. But we can have the spontaneous formation of cells, tiny objects, too small to see with your own eye, mostly. But those can now, because of this possibility of energy flows, we can have a spontaneous formation of cells. Then after that gets started, then complexity can grow and grow and grow because we can have more and more complexity, which we describe by information. As you know, we have DNA and so forth inside of our cells, and that controls it all. So is this an example of how there is a limit to what you can predict, but there are things you can describe. So here are diagrams of the circulation of the wind around the Earth. There are diagrams of the structure of a cell, a living cell, with its nucleus and its DNA in the center and all those kinds of things. And finally, the example of a more or less conscious creature, the laboratory rat, or you or me. We do whatever we please. We're not very predictable. And that's pretty important too. When you get enough complexity, there is no such thing as predictability. You can have a description of what happened, but you cannot always predict what will happen. So how did this all happen? We do not know. This is speculation. We imagine that we have a habitable world like ours, that some kind of complex molecules were able to be formed without presence of living materials, and they spontaneously were able to form into things that could become more complicated and grow into complex objects. So nobody knows how this happened. There's a lot of speculation, and a lot of scientific progress is being made to work out the details of how this might have happened. So here's an example of something that's quite important. If you imagine, well, the ocean could have just a lot of molecules, but when would you ever have enough molecules in one place to get the concentration up so something interesting could happen? So the idea here is in a small pond, perhaps it'll be dried out from time to time, or it'll be frozen from time to time, and the concentration of molecules on surfaces could increase enough that spontaneously a little cell could form, a little object surrounded by a cell wall, a little blob of oily materials containing other molecules, and that could get things started. What happens then, honestly, we do not know, but people are working on it, and by the time you're all grown up, you might be working on it too, or you might have the answers for somebody else. So what are the creative forces of the universe? Well, there have been living things here on Earth for about 4 billion years, which is most of the history of Earth. There are about 10 to the 30th power cells alive now, that is to say 1,000 billion. And over the history of our Earth, maybe 10 billion times as many as that. So 10 to the 40th cells. Each one of those is capable of solving a problem, responding in such a way that it can continue to live and reproduce. So that's all possible because of energy flows from the sun. And once it gets started, there is motivation in the sense, there are opportunities for communication between the cells, and it just can grow and grow and grow in complexity. So who knows how to describe all this thing, but it is a world, as I say, beyond science. We cannot predict. We can expect complexity to occur, but we cannot tell what it's going to do any more than you can tell what a human being is going to do. So who are we physically? We have, as you know, the structures of the body have been worked out. We know the chemistry. We know roughly what the brain is shaped like. And all that does not tell you how it works. We think sometimes that our brain is like a computer. It is somewhat in the sense that it's able to respond to the complexity of the world. And how is it made? It's a sort of a large version of an individual cell, which has sensors, feedback loops that adjust and control what the process is within to maintain the cell as something that's called homeostasis, to keep the cell alive by consuming food, transferring the waste products out, and doing all the things that it takes to still survive as a single cell. And now, of course, as you and I are made of about 30 trillion cells that are cooperating with each other, which is a mystery in its own. So, but people talk about our brain as though it's a supercomputer. Well, it's not. It is not something that you could compute. Um, Turing told us about the algorithms and what you could compute. But I think when you say the brain is programming itself all the time, it does not sit there. So you cannot ever really truly make an analogy between the brain and a computer. And you cannot upload your consciousness into the cloud as the science fiction stories tell us. So let me wrap up with a Fermi paradox. Enrico Fermi was a great physicist, and this is a picture from about 1940s when he was working on nuclear physics for the bomb program here in the US, which was an interesting project of its own. But he asked this interesting question. It was basically, if advanced civilizations can travel between the stars, why aren't they here? So perhaps the answer may be obvious to you, perhaps not. My answer would be they can't. The stars are too far apart, and no civil. I don't know if travel between the stars is possible, but the kind of travel that we can imagine is too slow. So perhaps we will invent and develop artificial life based on electronics, for instance, that can make the trip between stars, but perhaps not. At any rate, thank you for coming to the talk, and I'll be happy to talk with you about your questions. By the way,
Oh, John, thank you so much. And it dovetails so nicely with what Jim Green had to say just a week or so ago. Let's see. Do we have people? Let's see. Unshare your screen there, John, with
okay.
compiled version. I don't see any questions in the chat. So is there anybody that has a question for John that would like to delve a little deeper? All right. Well, I guess I can start.
Okay.
So John, with the James Webb Space Telescope, how small an object have we been able to see?
Oh my goodness.
Distant stars.
I suppose the smallest thing you can detect this way is a small planet around a small star.
Mm-hmm.
And we detect them not by seeing them directly, but by seeing the shadow when they block some starlight. So
Yeah.
we see objects that are smaller than Earth by this method, or I should say, we deduce that they are there. Here in the
Yeah.
solar system, of course, we have a few asteroids and comets coming through that are much smaller than that, and we can point the telescope at them. Perhaps the most famous ones are the ones that seem to be interstellar comets. So they're only a few miles across, and they go very rapidly through the solar system, and everybody wants to know what are they. But interstellar comets seems to be the story. Very unlikely that they're spaceships. Sorry.
So while we're racking up a few questions in the chat here, so 3i Atlas is on everybody's mind these days, and it's obvious it's not an alien spaceship. It really is a comet. Will James Webb Space Telescope get an opportunity to take an image of that, or will we be facing the wrong direction when it comes through?
Well, I think we got one. I think we got some pictures already. They don't know how soon we get to see it. Right now, it's quite close to the sun, right?
Yeah.
So we can't point in that direction.
Well, actually, yes, it would be on the other side of the sun. It doesn't actually come any closer than just inside the orbit of Mars, but the Earth has moved to the opposite side of the sun. So you'd have to look through the sun in order to be able to see it from
Yes. Yeah,
LaGrange
that's what I
two.
meant, right? Close
Yeah,
to the sun as it appears from here, is what I meant.
yeah. And of course, the result is the same. It would damage the space telescope if we were to
Yeah, we can't do
point
that.
it at the sun. So, um, okay, so we've got a few questions here. Um, let's see. Ray Wheeler, who's also a book, a scientist guest speaker, asks, is the universe still expanding? And what are the roles of dark matter and dark energy? Now, you touched on this really quickly, but Jim Green also did. And so
Yeah.
we're gonna see if you guys match up, by the way.
Yeah. Well, current evidence is that the universe is not only expanding, but expanding faster and faster every year. So yes, it's still expanding. And if the predictions hold, then after quite a few more billion years, we won't be able to see other galaxies except a few that are very close by.
Amazing, huh? That amazing that the night sky that we look at right now is, of course, what we see with the naked eye is all within our own galaxy, but uh, the night sky that we look at right now could go dark
Yeah.
if
Well,
we
there are
live
a
that
few
long.
things you can see the Andromeda Nebula with your own eye, even without binoculars.
Oh, that's a good point. Yeah.
But there are only a few things like that that are close, that are not in our own galaxy. Of course, in a trillion years, most of the stars will have burned out too, except for the smallest ones.
And maybe most of the humans.
Yeah, who knows what we're going to do?
Yeah. All right. Let's see. Vishal asks, what will be the role of emerging technology like AI in the advancement of cosmology?
Oh, well, we're certainly already using AI tools to analyze the images that we get to find the patterns that we might not have noticed already. Uh, Machine learning is very good at simulating the early universe better than we could do before, because it helps us solve the multi-scale problem. The multi-scale problem is the problem that you're trying to solve equations that cover this huge range of physical scales from millions of parsecs, which is to say many trillions of millions of trillions of of miles across, of kilometers across, down to tiny objects like asteroids and comets, which are only a few kilometers across. And you can't do it all once without some way of solving the problems on different scales separately and then stitching them together. So the artificial intelligence or machine learning is very powerful for that purpose. And as it happens, it's also doing quite well with weather forecasting.
Indeed. Yeah. And as the more we use it, the more problems we'll find to apply it to, right? So
Yeah.
let's see. Can we use the variational autoencoder? Don't know what that is. In order to analyze the image set instead of create time series analyses from the data taken using image set in order to explain the given phenomena in the image set. So,
Ah, well, to tell the truth, I don't know what the words mean either. Um, but I can say what we do try to do. Most of the things that we see in the sky do not change much from day to day. But we are moving into a new era of astronomy called multi-messenger astronomy, where we specially look for things that have changed. And we have just turned on a new telescope in South America called, and it is surveying the entire sky every 3 nights. So they expect to see 10 million things every night that are different from last time they looked. So some of those are going to be really interesting, and we certainly need the computers and the AI to help us find out what is the patterns of those things and which needs to be followed up with other equipment. So yes, that's a time series analysis, which is really pretty interesting. And it's at the limit of what we can do with computers.
yeah, and AI can definitely help us with that. Um, I was involved in a project called Atlas, which is the telescope that found the comet. It's actually a system of telescopes. There's two in Hawaii, one in Chile, I think, and the one that I was involved in South Africa. And yeah, their objective is to look for asteroids that are inbound, but they're finding so much more stuff with their full sky coverage, and they do 3 times a night as well. But they're specifically looking for transients and things that are moving, so that perhaps if there's an asteroid we haven't found, we'll see it in time to do something about it. So Julius asks a great question. This is speculation on your part, John. Are there theories of physics or astrophysics that JWST might actually help us to disprove or rewrite or maybe even confirm?
My goodness. Well,
or maybe you can't talk about it because it's in a paper.
Oh, no, no. And mostly when we build new equipment in astronomy, our hope is that we will find something nobody knew about. It's not so much to test people's theories as it is to discover things. And that's been the history of biology, the history of astronomy. Build new equipment and discover things that nobody knew about before. So it's hardly ever to test one theory against another. That's how it's been. We do have very powerful theories like what we now call the standard model of the expanding universe. Has 7 parameters and it matches observations extremely well. And there's also a problem with it, which is that we have multiple ways to measure the rate of expansion or to estimate the rate of expansion, and we're getting different answers. And the different answers are about 10% apart. And we think that's important. It might tell us something interesting. So we're not so much testing a theory as we're looking for things that don't fit. And so we have something that doesn't fit, and we don't know what to do with it yet, so we have to go get more information.
It's all part of science, right? Asking
Yeah.
questions, posing theories, making measurements, and then reanalyzing the results. And of course, sharing.
Yeah, so the way I look at it is theoretical predictions are helpful to tell you what experiment to try. But usually theories are not good enough to be tested. They're guidance as to what to look for. Because in our world of astronomy and in biology, everything is too complex to be really fully predictable. I can't predict what you're going to do. I don't have a theory of Jim Adams, and we don't have a theory of very many things in depth in astronomy. Even gravitation, which tells us how the planets orbit the sun, is still not a completely solved problem. It's not quite clear why the solar system is still here this way. Why are the 9 planets? Why does it seem that the planetary orbits are stable over 4.5 billion years?
Right. So you and I were just talking about this. Julius asks, how sensitive is the JWST in detecting distant objects? And will that be crucial in finding distant exoplanets?
Well, it's the most powerful tool we have right now. It's in space and it's able to see exoplanets, but only if they're very bright compared to the sort of small planets. The problem that all of us have in trying to find planets around other stars is that planets are small and faint and the stars are big and bright. And so it's trying to find something very faint next to something bright. So our job is block the starlight and see if there's anything left. So the tools are called coronagraphs because they were originally developed to study the solar corona. So we have them on the Webb telescope. Every new telescope seems to get one because it's the thing to try. But we don't have any yet that are powerful enough to see Earth around a star like the sun. So that's one way. Another way, which I've actually been working on, is called a star shade. If you could cast a shadow of a star from a great distance onto the telescope, you could block the starlight without blocking the planets. So the one I have in mind is about 100 meters across, It's 170,000 kilometers away from Earth, and it would cast a shadow on our biggest telescope in the world, which is called the European Extremely Large Telescope in the mountains in Chile. And if you could build it, you would be able to see an Earth-like planet around a star like the Sun in a 1 minute exposure. It would just be a little dot, and that would be well worth trying.
And there are missions. Trying to remember the name of the one that just decommissioned, that have told us where to look for some of these things, right?
Yeah, we've had two NASA missions that were based looking for the eclipses when a planet or transits when a planet goes in front of a star and blocks of starlight. You say, I know there's somebody there. Let's see what it is. How long does it take to go around the planet, the star? How warm is it? How big is it? All those things can be computed if you have enough of that information. So we've had two missions for that. And so far, as I said, it's not enough to see an Earth like around a star like the Sun. Oh, I should say, why do we care about stars like the Sun as compared to others? Um, the Sun is the only example that has a planet that we know of that has Earth, has life. So it has a long enough life so that something has a chance to grow. It has relatively friendly in the sense that it does not have a lot of solar eruptions coming at us to blast away our atmosphere. So the most common stars are very tiny stars, about the size of planet Jupiter, but hotter. But they are hostile. They blast away with storms of magnetized plasma quite often, and it would be enough to tear off the atmosphere of a planet if it had one. Um, which is not to say the planet couldn't be alive, it just would not be in the atmosphere. We would not be able to tell. So, quite possible, in my mind, that those planets out there around the M stars, the small stars, are alive, but you would never be able to tell.
I think you just sort of answered Julius's next question is, can it detect methane biosignatures in distant exoplanets as an indication of life in other worlds?
We can detect methane in exoplanets by this method, but only on large planets.
Mm-hmm.
So unlikely to be alive if it's only got a gas, like like Jupiter has.
Yeah. Um, and then before I switch to another person, he also asks, you want to summarize what you think the future of cosmology might be?
Oh, the future of cosmology. There is one big measurement we're still trying to do that we know we need to try. It's to measure the polarization of the cosmic microwave background radiation extremely well.
Mm.
There is a predicted pattern that could come from the very first moments um, of the expanding universe, and it would tell us about whether there are gravitational waves in those earliest moments, gravitational waves, large or small. Um, so it's a big mystery, but it's interesting because it tells you what is the nature of material, what's the nature of matter at that time. Here, as an example, in a gaseous material, we have only compression waves, um, sound waves. In a solid, you can have lateral waves as well. If I have a, a bar of wood and I knock on the side of it, sound waves will travel back and forth, but the sideways as well as compression waves. So that's the kind of thing we can answer if we can look for these signatures in the polarization. So that's part of it. We certainly also have big mysteries. What are the dark matter and the dark energy? And we have the tension, we call it which is the problem that we have different ways to estimate the rate of expansion, and we're getting different answers.
So as we start to wind up here, we've got a couple of more questions. These are more advisory, like to future watchers of this recording. And it's, what advice would you give to young students who want to work in astrophysics or cosmology or really any kind of space science?
Yeah, okay. Well, I'd say you have a number of choices to make when you're looking for things to do. First one is, where do you go to study? Uh, Go someplace that sounds exciting and try to find people where the people are happy doing what they're doing. It means that those people will be the ones that help you do your next step, whatever it is. So that's sort of number one. Do you like the people? Um, and then number two, are they working on something you think is interesting? And and so what would make something interesting? Well, it's unknown, it's worthwhile because it's important, and it's not too hard, meaning there's a chance that in our lifetime we could make some progress. So sometimes we're mistaken about these things, but I actually gave up on studying the cosmic background radiation after my thesis project did not work. I thought I'd work on something else, but then I got a chance to come back to it.
Mm. Yeah. So there's a little bit of opportunity as well as perseverance, right?
Yeah, so more opportunity than perseverance. But I think it's a matter of keeping your ears open for somebody that says, this would be fun, you want to try it. And you say yes.
Which is why we named the rovers on Mars opportunity, perseverance, curiosity.
Yeah,
Anyway, that's a
yeah,
whole nother session.
yes, indeed.
The the question from Manjula and from myself, really, as you've had a long career and you've seen a lot of things change in science, in space science, in technology. So the question is, what is the invention or the discovery that amazes you? Something that
Oh my goodness. I'm so astonished by microelectronics. Um, when I was a child, transistors had just been invented, and we had vacuum tubes already. And and a computer, I got to see one. A computer was an entire floor of a building filled with a few thousand vacuum tubes. And it was not nearly the thing you can do in your wristwatch today. So the progress in microelectronics has been the biggest surprise for me. So other things are also miraculously changing, but that's one where I think people had no appreciation of what the power of millions of engineers and billions of customers could produce.
Yeah, I had the same answer when I was asked that question years ago. I was a little bit behind you. Was in my bachelor's degree in physics in 1976, and I was playing with these new things called microelectronics chips in an electronic physics electronics lab, and I found that I needed to plan to do something when I got out of school. And so down the road, there was a company that made cash registers. And I thought, oh, well, someday these big clunky machines are going to be electronic. And so I trotted down the road and I said to the company, I'd like to work for you. They said, well, we're hiring, give us your resume. I did that. And they came back to me and they said, well, there's one problem. We're not hiring physicists, we're hiring electronic engineers. And so I ended up having to go with my second choice, which was building spacecraft for NASA.
And it worked out.
And it worked out just great. Yeah.
Yeah.
So let's see. I think we got a couple of more questions here. Yeah, Ray Wheeler just says thanks, John, for doing this. Oh, so here's an interesting question. Julius wants to know how winning the Nobel Prize in 2006 changed your life, and has it changed your view on science and philosophy?
um, well, to me, it was more of a recognition of the work that we'd already done.
Mm-hmm.
So it was not Well, it changes my life in the personal way. I have now many invitations to speak and travel. Um, but as far as I could, I just went back to work and said, my job is to finish the Webb telescope. And so keep on doing that job.
Yeah, I remember I was at NASA headquarters when you got the award, and John Grunsfeld, was it John Grunsfeld
Yes.
at the time? And and John was being quizzed by some staffer from the White House and trying to defend the science budget. And I remember him saying something like, well, we just won a Nobel Prize this week. Because, when somebody wins a Nobel Prize, everybody gets to take credit for it. And then he wanted to know, well, what does your agency do?
Yeah.
Yeah, it's a privilege to even have known you at the time and continue this ongoing relationship. Even now that I'm retired, looks like you're not ever going to stop working.
I like what I'm doing,
Yeah,
but I don't always do it the same way. But
yeah.
just as a sort of commentary on the importance of what we do, astronomy has been responsible for at least 3 or 4 Nobel Prizes in recent times. One
Mhm.
on gravitational waves, one on exoplanets, one on the cosmic microwave radiation, one on dark energy. So that's a lot. And so most of those are enabled by tools that engineers build for scientists to use.
Yeah, yeah. It's it's a privilege, actually, from my perspective anyway. It's a privilege to be able to do this for the American people.
Yes, and for the whole world.
Yeah. Um, all right, last question, and then we're going to call it quits. And
Okay.
Julius wants to know what the lifetime of the JWST is, and is it more than a century?
Oh my goodness. It will run out of fuel in a certain day, maybe 20 or so years in the future. Um, we use fuel for 2 purposes. One is to maintain the orbit, and one is to occasionally get rid of angular momentum that comes in from the sunshine pushing on the telescope. And it's not always balanced exactly over the center of mass. Um, so that we will use it up. It'll come out, and someday we'll say, okay, we have to say this is the end, and we give our last push to this telescope and push it away so it never comes back to hit us. So that's what end of life is for that telescope.
Yeah, yeah. And and of course, I I was on the engineering side. We always build in extra fuel beyond what the scientists say they want. So
Yeah,
just
we
just
did. We had a requirement for 5 years of life, an expectation of 10, and because we got a perfect launch from the Ariane 5 rocket, we are estimating at least 20.
yeah, that's fantastic.
Yes.
Awesome. Well, more great things to you, John. I hope it goes well.
Thank you.
And thank you for being willing to talk at Book a Scientist. For those of you that are online with us, if you listened to the talk, you should be able to answer the quiz. Manjula, is the quiz up?
Yes, both quiz and certificate, sir. They both.
Yeah, so take the quiz, pass the quiz, and you can earn a certificate. So,
Yay.
all right. Thank you, everybody, for
Dr.
being at Book
Michael,
a
thank you
Scientist.
so much for joining with us today. Really appreciate this.
Well,
Oh,
it's a pleasure. Good questions for all of the students, and thanks for you, Jim and Manjula, for organizing this for everyone.
yeah, you're quite welcome. I should also mention that on Saturday at this same hour, 11 a.m. Eastern Time, we're going to host Dr. Stephen Voles, who worked
Oh,
both at NASA as well as at NOAA. And he's going to be talking about why should we study the Earth from space.
yeah. So Steve also worked with me too,
Mhm.
so he can tell you more.
Yeah, we'll get the inside story from Steve. All right.
Okay.
All right,
Okay.
everybody, have a great
Thanks.
evening.
Thanks all. You too.